Everybody. This is lecture 2, which is entitled Statistics for One Variable. And this lecture corresponds to chapter 2 of the Minus the Math textbook. And so the key concept that we're going to talk about within this lecture are different measures of central tendency. And so here on this first slide, I have this question, which is something that we normally come across, which is, what is the typical value for a given variable? And when we're interested in asking what is the typical value for a given variable, we're essentially dealing with a type of measure of central tendency. And the most common measure of central tendency that we observe in practice is the mean, which is essentially just the average value, which has a lot of analytical advantage because it gives us sort of the most general and common measure of a given phenomenon. And so this should be review for a lot of you, but the way we go about calculating the mean is by adding up all of the values and then dividing by the total number of observations. And here in Greek lettering, the Greek letter mu is normally used to represent the mean. And it's equal to sigma, which is just a notation that means you add up all of the values of x. And then you divide this by the total number of observations, right? So that's taking essentially this statement here, but expressing it in mathematical notation. Now, another measure of central tendency that we come across frequently is the median, which is just the 50th percentile. And we calculate this by lining up all values from least to greatest and then picking the value that's in the middle. And if there's a case where two values are tied, we take the average of those two. And then finally, we have the mode, which is the most frequently occurring value within a distribution of data. And so there's a couple important things to know about how each of these measures of central tendency behave. So the first thing to know about the mean is that it's sensitive to outliers. So if there's an unusually large or small value, that can distort the average, right? So let's say we have a bunch of prices for houses that are clustered between $100,000 to $200,000, right? And then if we had a house that was $2.5 million, that's going to skew that distribution and yield a much higher mean value than if we excluded that outlier. Which, if we were doing that case, a more appropriate measure of central tendency would be the median because it's not actually sensitive to outliers. And then finally, we could use the mode, which we wouldn't want to use for continuous variables, mainly because of the issue of a lot of digits, but bins might be a way to get around that. But in general, we won't really use the mode as a common measure of central tendency. And it's important to know, as sort of alluded to on the previous slide, that there may be more than one mode. And so let's imagine that we were asked the question, how tightly is the data clustered around the center of the distribution? And we wanted to know, are most data points pretty close to the mean or median, or are they mostly spread out? And so for this kind of question, instead of a measure of central tendency, we want actually a measure of spread. And so some of the first most common and easy to calculate measures of spread that we had at our disposal is first the range, which is the maximum value versus the minimum value. But that doesn't necessarily tell us anything about whether most observations are close to the mean or the median. It just tells us, right, the range. Now, another thing we could use is the interquartile range, which is constructed by taking the 75th percentile minus the 25th percentile. And so the 25th and 75th percentile are calculated like the median, except for the fact that they mark the 25% point and 75% point as opposed to the middle. And then the interquartile range is actually depicted in a box plot if you looked at the edges of the box from the lab last week or the homework. But the most common measure of spread, and what we're going to be revisiting the most in this class, is what's known as the variance and the standard deviation. So we calculate the variance with this formula. Variance is expressed as sigma squared, and it's equal to the sum of all values of x minus the mean value squared. And then once you calculate that, you divide everything by the total number of observations. And so this is actually equal to the average squared deviation. Or in other words, it's the average squared difference between each data point and the mean. So it's effectively capturing spread. Now the standard deviation is actually just the square root of the variance, right? So the opposite of sigma squared, right? To remove that square term, you would take the square root. And so we have the square root of the sum of all the x sub i's minus the mean squared divided by the total number of observations. And a way you can think about this as is it's just the typical distance between a data point and the mean. And it's not exactly right in a pure mathematical sense, but it's a really good approximation. And so here we can see what happens when we manipulate the variance, right? So this is a variance of 5, or excuse me, a standard deviation of 5. And notice the spread is much smaller, right? But let's see what happens if we have a standard deviation of 10. See how the crest is a little bit less steep, but the spread is greater. And then here for a standard deviation of 20, an even flatter distribution and a greater spread.